bounding states in the circle compactification of target space.
Excuse me, you have a text message.
And then we discussed the self-dual radius R is equal to square root alpha prime in quantity. Okay? We realized that just to summarize, we realized that firstly the vertex operators could be written by treating x left and x right as completely independent fields. And the vertex operators were of the form e to the power I kl xl times e to the power I kr xr, where kl and kr are not necessarily the same, but took the form that we're familiar with, right? This is n by r plus minus omega r by r, w or m r by r. Okay? And the rules for contraction of these XL and XR, which is the holomorphic parts of the rules for contraction of the full field. Okay. We then started looking at the self-dual radius in a little more detail, and we defined these three: j plus is equal to the power I, then square root 2 by alpha prime x, 2 by x, j minus is equal to xl, of course. So, when I say x, I mean xl. The whole j minus is equal to minus 2 by square root alpha prime x, and jz. Can somebody remind me of the normalization, please? I by square root alpha. And at the end of the last class, we demonstrated that these operators obey the SU2 algebra. Namely, we demonstrated that we made these linear combinations. We went j plus is equal to jx plus ijy, j minus is equal to jx minus ijy. And then we found that ji of z, j of 0 is equal to half z squared delta ij plus alpha. Okay, and we discussed a little bit the significance of. Okay, so at the end of the last class, I started telling you about some terminology. So these operators, these three operators, J1, J2, J3, are each holomorphic operators of dimension. Okay, more precisely, the operators of dimension 1, 0. I needn't even say the comma 0, because since they don't depend on z bar, okay, in a unitary theory, they necessarily dimension 0 and z bar. Okay, if you remember, the early part of our course, we proved this. The only operator that was independent of the field coordinate was the identity operator. Okay, any operator that was independent of the field coordinate necessarily had 0 and therefore the identity operator. And then there was a square root of that statement, which was that any operator that was independent of z bar had to have weights anti-coordinate weights here. Okay. So these operators each have weight 1, 0. There are the corresponding anti-holomorphic operators that weight 0, 1. Okay, and we had these 9 scalar fields. Which were ji of z, g bar, k of z bar. Vertex operators were j of z, j bar, k of z bar. And then we also have the SU2 and SU2 gauge boson vertex operators. VI Z del bar X mu, and linear combinations of these with VI bar delta. These are all one vertex operators, and these were the operators that described that were the vertex operators for the SU gauge bosons in space-time. Okay, any questions or comments about this? Okay, now the fact that these gauge bosons describe an SU2 times SU2 gauge scale in space-time is sort of intuitive what you say precisely, but more but can be checked by direct calculation. And what's the idea of the direct calculation? The idea of the direct calculation is this. Let's say, in order to understand what the interactions between gauge bosons are, you need to calculate, for instance, the three bosons scattering vertex. Scattering. Now, as you know, this is all close to the stuff. Or as you know, what you need to do in order to do that is to calculate the 3-point function of the 3 vertex operator, each of which is fixed at 0, 1, infinity. Okay? But that 3-point function is proportional to epsilon ij. That you see from the fact that the 3-point function between 3 operators is the same as the OP coefficient after factors of z. Right? If you wanted a 3-point function here, you put another j, take expectation value, and you get from j is equal to delta I. Okay, you get this. Absolutely. So 3-point functions of these gauge boson vertex operators have a part coming from here and a part coming from there. The part coming from there is what we've always had. It's just the del x. We give you all the space-time index structure of the gauge boson. The part coming from here is the flavor part. It's the color part of the gauge. And that has an epsilon ij, okay, which is a structure group of SU2. Okay? So you see, from one should actually do an obvious calculation here of the factors, right? So, but you see the structure. It's clear that because we've got current algebra on the world sheet, we're going to get a gauge symmetry in space. Because the gauge bosons that are associated with these currents, with these current operators, will scatter just like gauge bosons. Gauge bosons associated with the group in question. SU2. Okay? So there's a tight connection between having this kind of operator structure on this kind of operator structure on the worldsheet and having gauge invariance. Okay? And the gauge group is the same as the group that we are seeing. Okay? So at this point, so this is something we mentioned before, but now we see the reason for it. At this point in this moduli space, namely when the circle is compactified in a circle, when the circle is compactified with a compactification radius equal to square root alpha prime, we have a new non-abelian gauge symmetry in space time, and this gauge symmetry is SU2 times SU2. Okay. Now, it is not really obvious that all of them are all the strings segment is the current multiple function. Yeah. How do you know that everything is in the correct multiplet structure of the it's because J, let's say the 0 mole of, you see, this current here is a conserved current. Okay? And the 0 mole of this current gives you a conserved charge. Okay? This conserved charge has a certain algebra, namely the SU2 algebra. Okay? And every state in the worldsheet there will therefore transform into representations of this. Well, what I'm saying is very simple. I'm saying that apart from current algebra, there is in particular the global symmetry of SU2 rotations, just on the worksheet. You remember we looked at the mode expansion that came from here? Okay? We looked at the mode expansion that came from here.
And then we got the central extension.
We got the central extension, but now focus just on the zero mode part of that. In particular, we had operators, okay, that implemented the SU2 count, that implemented the SU2 algebra, just the zero modes. Also, the zero modes of J0. This part I haven't explained carefully. This is the Sugawara construction that I alluded to last time. We'll come back to that. Okay? But the zero modes of J0, but anyway, this in this particular example, commute with L0. Because it's the zero mode. L0, JM0, M times J. Okay? So, firstly, the fact that, okay, so what do we have? The Hilbert space that you get by looking at this theory, okay, has in it operators whose combination relations implement the SU2 algebra. Moreover, these operators commute with LC. Okay? So, all states in the system can be arranged in representation of SU2. And moreover, physical states are also in representation of SU2. Essentially because this commutation is based. Okay? So, what I'm saying is that the SU2 symmetry structure of the worldsheet is manifest. You see, what we call is a huge symmetry actually. So, everything transforms in representations of that symmetry. Okay? All that remains to convince yourself of is the fact that the physical state condition also commutes with that symmetry. Okay? And that's true. It's more or less, more or less follows from the fact that T is a singlet vector. Why is the atomic step a singlet? Because of
okay, just from LMG.
From exactly.
LJ.
Yes, from the LJ commutator. It follows. Of course, you can check everything in this particular example very explicitly. Because you know what T is, you know what J is, just check. Okay? And we've seen as an example, for instance, that part of the physical state condition is that you have a certain value of L0 for the oscillators. Okay, the mass square L0, and that commutes with the SU2. Okay, but the structural understanding of this is best. I was not planning to discuss it now, but let me just give you 2 minutes on it. It's best, how the structure goes through, the fact that the connection between the current algebra and the Virasoro algebra. There's a tight connection between these two. Okay? And that connection basically is the statement that it's possible to write the Virasoro, the stress tensor, as a quadrature of these currents plus something that has zero OPs with the currents. Okay? And when you go through that construction, this is what's called the Sugawara construction. Okay, the connection between the stress tensor and the currents of the current algebra. Okay? And when you go through that construction, once we go through that construction, the answers to your question become really manifestly clear. Okay? Basically, okay, but let's postpone that for a future point. You see, it's possible. Basically, we've so far been discussing representation theory of the Virasoro algebra. But there is a finer representation theory. Okay? All states in a conformal field theory like this can be arranged as descendants of primaries of this algebra. Okay? Where a primary of this algebra obeys a condition like J times phi is equal to representation matrix acting on phi divided by Z plus regular. Okay? So just like every state in a conformity theory can be arranged in representations of the Lira structure. Every state in a conformity theory that implements a current algebra can be arranged in terms of primaries and descendants. Okay, let me just give you 2 minutes now. Okay, let me give you 2 minutes. Okay, so the set of all operators or all states, same thing, in the field theory, can be labeled as follows. So there is a bunch of operators that are distinguished. They're called primary operators. Okay, these operators obey are labeled by phi r and t, where A is a representation index, in this case question 2, R is the label of the representation. Spin. Okay? The primaries obey the following commutation relations. Ji on phi of z, j of 0, and A is equal to R I AB phi b of 0 of z plus θ, where R is a representation matrix for SU2 in that representation. And every operator in the game is a descendant of one of these primaries. Okay, by descendant I mean can be built by acting on one of these primaries with one of the lowering J operators. In the same way that we talk about descendants of the Venus. Okay, so that's the full operator space of the theory and full Hilbert space of the theory. Okay, now, in particular, of course, if you look at a particular level, you get representations of the global SU, but a much bigger representation structure. Now, so this is true. Now, what's sort of interesting is that there is a relationship that goes roughly like this. The stress tensor is Ji times some normalization. Okay? Plus a function of these. Okay. That has no boundary below these with the J's. This structure guarantees that whenever every primary of the SU2 algebra is a primary of the Lira structure. Okay? The reverse structure. You can have primaries of the Lira for algebra, but not primaries of the SU2 algebra. Okay. And basically this understanding this sort of tight connection allows you to demonstrate that the SU2 action in a cleaner way, cleaner than we've done so far, commutes to the physical state condition. Basically from a relationship. More or less. Okay. So we will at some point, this is the material that's covered in chapter 14 or 15 in volume 2 of Kulshinsky's book. And since we're at this point trying to go linearly through Kulshinsky's book, let's postpone this to when we get to it. Really, this is an interesting but technical algebraic discussion. It was very interesting and we'll talk about it at some point in this course, which will probably go on for another year. I mean, as long as you guys have interest. Okay. But for now, let's forget about it. So I'll listen to our immediate discussion. Yes?
Now, okay. Now, what about the tachyons in this theory? I mean, there are additional tachyons.
There are additional tachyons.
So, I mean, how are they related to, they say, J plus and J minus?
Right. So the additional tachyons are matter fields that transform under this J plus. You want to know whether they're correct? Well,
whether they are the J plus J minus.
No, they're not the J plus J minus because the tachyon fields. See, J plus J minus have dimension 1. Tachyon fields correspond to vertex operators that have dimension smaller. Okay, we got this J plus J minus, if you remember, by taking n plus m, where n is the momentum quantum number, m is the winding quantum number, to be 2. We get the tachyon fields by taking n plus m to be 1. Okay? So the tachyon fields in the problem will have either n equals plus minus 1 and n equals 0, you know, yeah, basically n equals plus minus 1 and n equals 0, or n equals plus minus 1 and n equals 0.
Also, you won't, I mean, these J's themselves won't be primary operators themselves, right? In this.
They're not primaries under
Under the current.
but they're primaries under the Vira.
Yeah, that's right.
For physical state condition, we only need the operator to be primary under Vira. So, one shouldn't argue that the J's are not good vertex operators for states in theory, because they are, they make up the games. It's clear the primaries are under Vira, right? Because all these operators we individually checked out. You can also check them abstract construction, but that's not it.
There is a bit of a descendants.
The descendants under SU.
Right.
But we don't care that. See,
So then, I mean, you want, if these are, I mean, if this can be a vertex operators, then there will be physical states corresponding to those vertex operators.
yes,
And those states,
the gauge goes on, and the master scalar phase, right? We'll discuss that. They definitely
they can be primary.
They not only can be, they are.
Yeah.
Okay? So, in fact, it's generally true that the J's are primarily under the. You see, the J's are honest dimension 1 primary operators under the. Okay? They're honest, you know, vertex operators that you can put inside your scalar. Okay. But, just to go on track. So, the tachyons, in fact, will transform under the 2 times 2 of x equal to x. They will be spin out and spin out. But, you know, as is usually the case, tachyons basically are not going to correspond. You know, while they appear in the bosonic string, where we look at such an analogous construction in the superstring. Okay, this will be in the context of, for instance, the heterotic string, as we discussed. Talked about the superstring. There will be no analogs of the tachyon operators, which is why I don't spend my time here.
Okay, but I mean, is there any way of understanding why there are additional tachyons? I mean, why there is additional instability then?
You see, roughly speaking, it's clear. I mean, it's a matter of numbers, but roughly speaking, it's clear. You see, we have a basic tachyon. Okay? Now, one thing you can do is to look at Kilnsat-line modes of that basic tachyon. If the circle is very, very large, a lot of Kilnsat-line modes will also be tachyon. No, of course. You see, we're looking at modes that have n equals plus minus 1. N is the momentum. It's the momentum number of the identity operator. And therefore momentum of the tachyon. Let's write down the vertex operators. Okay. So let's first look at the states. Okay. So Kn is equal to n by n plus minus Kn r is equal to n plus minus m 1 over square root. Okay. Now let's look at the modes with for instance n is equal to n. Okay. This is KLR equals 1 by square root. Okay? And if we're now looking at the states with no oscillator. With no oscillator inside. Why is that? It's because it's a mass square formula. But if you want a tachyon, the mass squared is equal to KL squared by 4 alpha prime. No, there's no 4. There's no. Sorry, mass squared is equal to KL squared by.
It is just K squared plus 4 by alpha.
Plus 4, yeah. Okay, let's write down mass squared. Alpha prime mass squared. Sorry. Yeah, alpha prime is squared by 4 is equal to KI squared plus 8. And let's put the nominal. 1 by 4, sorry. Again, similarly for K and similarly for K. Okay, now if K and K are any non-zero number, the minimum value for N or NR is 1. Apart from 0. The minimum non-zero value is 1. If K and K are 0, then N equals 1 will give you a master state. But if K is something non-zero, then N equals 1 or any higher will give you a massive state. So when we're interested in the tachyons, we have to have both N and NR equal to 0. Okay? Therefore, full vertex of. Okay, so for instance, one operator is N equals 1, N equals 0. Now what does that give us? That gives us Kn is equal to Kn is equal to 1 is equal to Ki. 1 by N. Okay? Now what's the vertex operator for this? The vertex operator for this is simply nothing, no del exists.
Alpha prime K squared.
Alpha prime K squared. Okay. Yeah. The vertex operator for this is e to the power of I, and we had 2 by square root alpha prime before, that 2 has gone away. That's the only difference, right? K less than half compared to N is equal to N is equal. Right. Square root alpha prime, that's it. Okay, times e to the power I x r by square root alpha prime in this case, which is just e to the power I by square root alpha prime and x. This is exactly the tachyon vertex operator, with momentum equal to whatever it is. 1 by r. No r. Okay, so this is the first Coulomb-Saclin mode of the tachyon.
Yeah, which has become tachyonic here.
Which will always, you see, so what's going on? The thing that's going on is this, that if you've got a field that has a negative mass square, so let's see what is the mass square from the lower dimensional point of view of a field with basic bare mass m0 square. The lower dimensional mass square according to the Coulomb-Saclin formula is m0 square plus n square by r square. Now what's going on is that m0 square was equal to minus 4 by r square. Okay? R square in this situation is alpha. So the first mode, the mode with n equals 1 of the tachyonic field is still tachyonic. Because this overwhelms this. It's just the first Coulomb-Saclin mode of the original tachyon field. So that's one of the 4 states that I got. Okay? This would have been, this is not something surprising at all. Had the radius been any large number, we've got plenty of Coulomb-Saclin modes at tachyon. Had this radius been very large, instead of alpha, right?
Okay.
Suppose it was 200 square times alpha, right? We'd have got more than 200 tachyonic modes. It's just that the extra energy that you get from momentum in the additional direction is not enough to overwhelm the negative energy of the mass. Okay? So that Coulomb-Saclin modes of the tachyon are also tachyonic, provided the circle is not too small. It's clear. It's a number of CMC values of the circle is too small. And we just done that number, okay? And it's not too short. Okay? Now, let's return to the line view. Okay, so I talked about 1, but actually there are 2. So you can have Coulomb-Saclin mode n equals 1, n equals minus 1. Now, similarly for the wind,
Only that there will be a lot of them for small r.
Exactly. There will be lots of things cycline modes for small r.
Also winding modes.
There are lots of winding modes for small r. Now, is this thing small enough to have at least one winding? Let's check. Okay? So,
Basically, n square is equal to w.
exactly. You just get n squared replaced by w squared usually. You can do that counting. Get n squared replaced by w squared. And again, w equals 1 and minus 1 works. Okay? But none of the other works. Okay? So the four additional tachyonic fields are simply the Kaluza line and winding modes of the basic. Momentum adds to the mass of the field, winding adds to the mass of the field, but at this point, when n and w are 1 each, it doesn't add enough to stop them from attacking. But when n and w become 2 each, you see, it just cancels. And then the field is not tachyonic anymore. And that's what gives rise to our 9 scalars and our 6 scalars. Well, some of the 9 scalars and some of the 6 scalars. Okay? So the massless scales also from this point of view are excitations of the basic tachyon. Some of them. Now you may wonder that because of that, this whole phenomenon is trying to go unexplained. You may wonder that in a situation where there are no basic tachyons, you won't have this phenomenon. We see that that's not true in an appropriate way. We'll examine this. When we get to so
what happens, like in standard ratings where these Kaluza modes are actually massless, there also will get some enhanced.
Where these Kaluza line, where the first Kaluza line mode is massless. Okay, yeah. So when the first Kaluza line mode is massless,
we replace it by n square by r square again, and then there is some r. This expression vanishes.
Yeah. Yeah, good question. Let's see how it goes. You see, we don't get it. Oh. Just. As long as you've got these massless vector bosons. Let's single SE. You see, because there's no democracy between N and W at this new new scale. Okay, so
but will we get a vector boson?
I think we will, right? because, but you asked me what the origin was. I haven't thought about this. Okay? But let's just see. So, effectively, the question is are these modes? Are these modes here? E to the power I 2 by square root alpha prime x in your spectrum. Okay, this plus minus and x. As long as that's in your spectrum, you're going to get the current algebra and everything is square. Okay, now we got this in our situation at n equals 2. But if you are a radius in which you get this at n equals 1, that will also. So let's just work that out.
But you would get plus 1 by 2. You would get 2 by.
What?
You would get I by root alpha prime.
No. If you want that to
equal to 1.
Right. But you also change your radius, right?
Oh, yeah.
Basically, you know, you want it to be a radius where the n equals 1 mode was fixed. Okay? That's saying that you're at a radius where this is the n equals 1 mode.
You need to get this.
It's going to be exactly this. Okay. So, but you see, what you're going to get is n equals plus minus 1, but not w is equal to plus minus 1. Okay? And then you'll also have, of course, the delta x. So I think you'll get just a single SU2 rather than the SU2 times SU2 kind of structure that we had before.
Okay. So this is like, you have reached one of the SU2.
Exactly. You have a place where of the two SU2 times SU2s, you've restored some linear combination or something like that. Yeah, so it will be exactly like that. Yeah. So in general, there are several points in this compactifications. There are several points of partially restored symmetry. Okay, but the maximal symmetry in this situation is SU2 times SU2. Right. As we study more of this, you see, we'll study compactification of general. We will address similar issues in more detail. Yeah, I think that's okay. Good question. Other questions?
Now, this algebra, this JI algebra.
Yes.
How we will expect it to get deformed once we deform it outside the self-radius.
The operators that generate this current do not. I mean,
but they are not available as states.
They're not available as states, right? Right. So the conformal field theory outside the center, a little away from this cellular point, does not have this SU2 symmetry. You know, the vertex operators that would have when integrated giving you the SU2 currents are not good vertex operators. Can't act in those states.
Yes, but there will be some vertex operators, I mean, which are good.
But they don't obey, you know.
So they should obey some kind of a deformation of this algebra, of this OB, right? In the sense that you put R equal to. Basically, you take the actual conserving mode.
Yeah, that is going to be very different. You see, because these are not dimension 1 operators. Okay, so the structure is going to be very different. For instance, there's no zero mode for that. The whole thing is going to be very different. It's a very severe explanation of the structure. It was very important what we did that these were dimension 1 operators. And that works exactly like this.
What I was asking for is that from a space-time theory point of view, you would expect that, like if you had a gauge theory, it instant or something like that.
Right.
I mean, there will be some relations which will still be remaining.
Yeah. So what's going to happen is that you'll get from space-time field theory point of view, you're going to get,
for example, there'll still be ward identities. Now, what I'm asking is, even if you do about vertical safety also, it's just that is there some remnant of this, broken space-time basically? which is remaining as some kind of OPD.
Yeah. Well, right. So, well, certainly there will be some. So let's see. So, from space-time point of view, what will happen to these? What will happen to the charged gauge bosons is that they will become massive.
Yes.
Okay, this will be the heat. Now, if you know the basic 3-point vertex operators of the original object, you also know how W plus W minus A scattering is. Okay? So that structure will continue to work with the 3-point functions of these operators. So certainly there will be some relationship. But if you're asking for a tight mathematical connection, I'm not aware of. I'm not aware of. There may well be for somebody studying how this operator algebra is formed. What the right version of that question is as you go away from it. You know what should happen from space-time that will be reflected on the whole sheet. But I don't know. I don't have anything more.
Really, the field spectrum at some general radius doesn't seem to have a lot of structure, but we should expect that, this would be just expect that there should be some kind of identity.
Yeah, but it's not manifest structure. It's not like the thing will appear in representation space. It's true that there should be some relations, but they're quite subtle things. It's not like you get multiplets of the same energies. If you search for those subtle things, I think you'll find them. I think basically, it will be the fact. Okay, I think basically it will be the following fact. That if you want to go to a larger radius, okay, then let's look at that in terms of the theory at the center. Okay, so what is the operator that deforms the size of the radius? The operator that deforms the size of the radius is just Jz. Because the radius operator, you see, so suppose you wanted to work with with an operator. Okay, so say we were in space-time and the worldsheet theory had del x with this in the space-time, some constant g. The value of dB gives you the radius. So if you want to change dB, the operator you have to add to your worldsheet theory is del x and del y. Okay? But del x and del y is simply Jz and Jz. So the relationship you are looking for is going to be the fact that the worldsheet theory at an arbitrary radius is the worldsheet theory where SU is manifest, deformed by Jz. Okay? That will then give you some connection between the original symmetric structure theory, deformed in a very particular way. And that will lead you into the space-time case mechanics. Okay? So these two things will mathematically go together, but I don't know in more detail. So I haven't tried to figure it out. But that's basically it.
But this is a very specific, here we know the theory, here we know what the deformation is. What I was asking was, is there some level, for example, we can write down the current algebra, we can write down a central extension. Can I understand from an algebraic point of view what are these mechanisms?
But you see, the Higgs mechanism will always be like this. Because the deformation of the theory is always by a 1-1 operator. You see, suppose you've got a conformal field theory and you want to deform it away to another conformal field theory. The deformation is always by adding some 1-1 operator. Now, what 1-1 operators are guaranteed to have in your theory? There could be coincidentally. But what 1-1 operators are you guaranteed to have in your theory on general grounds? It's bilinears of the current. Okay? So this structure will be quite general. If the Any other questions about this? Perhaps facing the good effects of the set of exams. Many more questions than before. Okay, good. Other questions about it? Okay, good. So let's get back to our discussion. Okay, let's get back to our discussion. Okay, so we've worked on this general structure. We've got this nice asymmetry in space-time and so on. Now I wanted to go back to our discussion of residuality. Okay, you might remember that we talked about how the spectrum of the theory You might remember how we talked about how we discussed the spectrum of the theory, the spectrum of our worldsheet conformity theory, the space-time spectrum associated with that was invariant under R goes to alpha prime by R. Okay, I now want to give you a very general argument that this invariance, firstly, is an exact non-perturbative symmetry of string theory. By non-perturbative, I mean non-perturbative even in the string type. Okay? And moreover, there is not any other symmetry that's a gauge symmetry. Now you may wonder, how the hell can I give you this very general non-perturbative argument since I haven't told you what non-perturbative string theory is? And the answer is that, well, assuming the consistency of string theory, I'll give you a very general argument. And the argument goes as follows. Look, as we just discussed in the answer to the Adam's question, the deformation of the theory to a larger radius away from central point is generated by NX negative. But the deformation of the theory to a smaller radius, okay, under the same to a smaller radius is generated by minus of that, minus NX. Okay? Now, maybe we'll put in numbers in it. Now I want to argue for you that these two deformations are actually the same. How do I do that? Okay? How do I do that? I do that by noting that look, this operator is Jz, Jz. This operator is written as minus Jz, Jz bar. Now, minus Jz is what you get from Jz by doing a rotation about the x-axis by 180 degrees. Imagine the axis rotate by 180 degrees, and you get so this thing is symmetry equivalent to this thing. So these two infinitesimal deformations are in fact the same. They're symmetry related. They're related by an SU2 transformation. Is this clear? Now, we realize that what was an SU2 transformation, global SU2 transformation on the world sheet of the string, becomes a part of the gauge symmetry. Part of the gauge SU2. Okay? In space-time. Now, the only known way of having having a consistent theory of massless vector gauge is to have a gauge symmetry. Okay? Because of this, assuming that string theory is a consistent theory, the gauge invariance that we've argued about from classical string theory must be the exact non-perturbative invariance of the full space-time theory. Okay? So, this symmetry, which is clearly symmetric from the point of view of a classical world sheet, SU2 rotation, okay? Which is already enough to tell you that in classical string theory, it's an invariance of the theory. It's a symmetric of full quantum non-perturbative string theory. Okay? And in fact, is part of what we regard as a gauge symmetry from space. Okay? So, while I've only given you the argument for infinitesimals, okay, I encourage you to try to turn this into an argument for full finite, the full finite transformation. Okay? I've given you the argument that R into 1 plus epsilon, R is identical to 1 minus epsilon. Okay? Try to turn this into an argument. Try to arise an exercise to turn this into an argument for the finite transformations. Okay? But this then immediately tells you that T duality, this equivalence of gauge of string theory at radii square root alpha r and square root alpha prime divided by r is an exact non-perturbative symmetry of string theory, and in fact should be treated as a gauge symmetry. That is, theories with radius r and alpha prime by r should be thought of as different descriptions of the same physical system. Well, at least to the extent, I think that's accurate. So in particular, for instance, if you wanted to allow, you could, if you wanted to study a circle that winds around some other circle, and as it winds around becomes a circle, the circle size that was winding goes from R to alpha prime by R. You could imagine twists by T duality, okay, in a physical configuration, because this is a continuous physical configuration. Yeah, this is just a throwaway remark, but the remark went as follows. Look, suppose you've got a space, okay, with two circles, okay, and the size of the first circle varies as a function of where you go on the second circle. Okay, so it's a fiber kind of situation. It's not a direct product, but okay. Now, normally you would impose that if such a thing happened, you would impose periodicity of the size of the circle. That when you come back to yourself under the second circle, the first circle comes back to the same radius. Okay? That's the situation that will give you a smooth geometry. But remember, R and alpha prime by R are identical configurations in string theory. So in string theory, we would allow situations where the circle did come back to itself after going around the second circle, but came back to alpha prime by itself. Okay? So that's the content of saying that the T-duality symmetry is a gauge symmetry. These things are treated not as equivalent but different physical configurations. They're treated as being the same physical configuration. Okay, these are mapped to each other by a gauge. Is this clear?
And that in discretely planning would be like having something like some polynomial about x, and an acyclic polynomial which just rotates, which is go around.
Well, yeah, at the self-dual point, alpha prime by R and R are the same.
Yes.
So you will have to have a holonomy in the broken theory.
Yes, it's a polynomial.
Yes, I think that's basically right. Okay, so now, so T duality is the first of the space-time dualities that we will encounter in our study of string theory, and it's the simplest one. It's the simplest one because we see it in string perturbation. Okay, as we carry on with our study of string theory, we will encounter more exotic, more interesting dualities, S dualities, which are not visible in string perturbation theory, but which is other things. So now let me get back to the main plan of today's lecture, which was supposed to talk about overflows. Okay, so let's start. Okay. So in the rest of today's lecture, I'm going to discuss another compactification of string theory, sticking at the moment still to closed strings. Okay. I'm going to discuss another compactification of string theory, which are overfold compactifications. Okay. So consider the symmetry operation of the Friedel theory, which is x goes to minus x. It's clearly a symmetry of the worldsheet action because the action is quadratic in x. Okay, now what we're going to try to do is to gauge the symmetry of the worldsheet. Okay? In the same way that we gauge the translation symmetry, x goes to x plus 2 pi r, in trying to make a space-time circle compactification of string. Is this clear? So we said the configuration x was the same thing as x plus 2 pi r. That gives us a circle identification, allow winding states and so on. Okay? What we're going to try to do is to take this discrete symmetry of the theory and promote it to gauge invariance of the worldsheet theories, not gauge invariance of space-time. Okay? And see what comes up. Is this clear? So from the point of view of space-time, what we're doing is taking a coordinate which has its target space the full x-axis and making the target space the half loop. Because x is the same point as x. We're putting a sort of wall in space. Okay? Deformation of what?
I mean that whatever theory we get by dealing with
will be connected to the theory we started with? Sorry, what's the question? It's not a clear idea. It turns out the answer is yes. Okay? But in order to, basically it's a limit of some these kind of overfolds emerge as limits of geometric compactification. We'll see that as we carry on in our study. But the reason we're studying it is the answer to that. Yeah, so it's a good question. Okay. Okay. So now, at the moment, this is mathematical exercise. We want to try to study this gauge version. Okay? And you see what space-time interpretation is. We'll also, by the way, points immediately after doing this, we'll study the combination of an overfold and a circle compactification. But let's first, just be sort of clear. Just look at the overfold without the circle. Okay. So, what do you get? Now, just like in studying the circle compactification, there are two effects. The first effect is that not all states without the overfolding remain states in the theory. What was that effect for circle compactification? That the states have to respect the periodicity. And that gave us a quantization of momentum. It took the continuous momentum without the compactification and made the momentum equilibrium. Right? Is that clear? That's what worked when we looked at. Oh my god, sorry. Before moving on. I'm sorry. I'll rewind for 5 minutes. There was one more thing on the self-fluid radius that I wanted. Wait, so this is just a rewind. Okay, so there's something else I wanted. And that was this, let's say it fast. You remember we had these massless scalar fields, MIK, okay, which were in 3 cross 3 of SC2 times SC2. Okay. Now, the fact that the massless tells us that from a space-time point of view, the effective potential for these fields is 0 at quadratic. Right? That's what it means for fields to be massless from space-time. Now you could ask whether there were more, whether the effective potential for these fields is just absolutely flat, or there's some higher values. Okay? And the answer to the question is that there is a higher value. And that's very easy to see. Suppose we try to calculate the 3-point function of 3 of these objects. What would the answer be? What would the answer be proposed? So what are the vertex operators? Say ji1, j bar j1, ji2, j bar j2, ji3, j bar j2. We're going to compute the vertex operator, 3-point function of these. What are we going to get?
So these three J's to give you epsilon I as a
exactly.
I1 length epsilon of all the length epsilon.
Exactly. So that tells you that there's a term of the potential mi1 j1, mi2 j2, mi3 j2. Okay? So the same calculation that told you that there was a 3-point function of the gauge bosons that gave you the structure constants of the gauge group, some double here to give you a potential for these scalars. Right? It's a 5-cube potential. Hey, there's no claim that there isn't a higher order potential. Okay? But there is this. Okay. Now, okay. Now, given this potential, one might ask, you see, there's an interesting question, and that's this. The interesting question is, what are the various theories you can get by deforming away from the self-dual point? Okay? What are the various theories you can get by deforming away from the self-dual points by adding one of the massless vertex operators? So adding one of these ends to the okay? Now, from the point of view of space-time, that becomes equivalent to the question, what are the deformations, what configurations of these ends obey the equations of motion of the space-time theory? Okay. Now, I'll say a couple of things, part of which I'll leave as exercises. The first one is that I want you to show that you can always use an SU2 times SU2 to set mi j bar to be direct. I need to take the form m11 and m22. Just as a sanity check, let's do some counting. The arbitrary mij has 9 components. SU2 times SU2 has 6 components in it, and you can easily convince yourself that none of these generators in general are annihilated by an arbitrary variation. So there are 3 components in the values of m11 and m22. So the counting works. Right? It's possible that you could generate every 9 cross 9 matrix m11, m22, m33 by SU2 and SU2 rotations of these. And the claim is that that's exactly right. Okay. In this case, it's like a real version. That's how you done, right? Okay. Right. But you see, configurations, all configurations can be brought by gauge transformation to something of this form. So things that are gauge equivalent are of course gauge equivalent. So what inequivalent ways of deforming away from self-dual point will be generated by the values of M11, M22 and M3. Okay? Now, we want ways that leave that go along the flat part of the potential, that solve the equation of motion in space-time. Okay? So let's see what the equation of motion tells us about the configurations M11, M22, and M3. About the fields M11. Okay. So, the space-time potential was basically the determinant of this object. Okay? If we differentiate with respect to any given matrix element, we differentiate the determinant with respect to any given matrix element, we get something proportional to, we get the minor of that. So let's look at the equation of motion that comes from M11. It's a product of M22 and M3 in this configuration. Okay? So the equation of motion that comes from M11 tells us that M22, M3 times M3 is equal to 0. Similarly, we get three other equations. So we get the equations M11, M22, M22, M33 is equal to M33, M11. How do we satisfy this condition? Of course, it's obvious solution which everything is 0. But if you look at it a little bit more, because it's already a product of two things, any one of them being 0, any two of them being 0, any two of them being 0 also satisfies the equation. Okay? So, for instance, M11 is equal to M22 is equal to 0, satisfies the equation, which can permute. That permutation is gauge. It's changing x for y and y for z. Okay? So, there is the only solution to this equation, up to date transformation, is M33. M33 not equal to 0 is, M33 is JZ bar. So the only already calculations we've done have demonstrated that the only possible exactly marginal deformation away from the SU2 and SU2 point is by JZ. Or of course gauge rotations there. For instance, one gauge rotation of this would be JX dx bar. Okay, then that will be more common. Okay. So this is the only possible exactly marginal deformation away from this SU2 and SU2. Now, that is an exactly marginal deformation is manifest by the nature. Because we've seen that what this does, it just changes the size of the circle. And conformal field theory is that all of the radii of the circle are exactly conformal. Okay? So we've got the necessary and sufficient data. If we're asking, what are the various possible ways of deforming the theory at the self-dual radius, the only possible one up to symmetry is by JZ. And that one is an exactly marginal deformation. Okay? So while we had this 9-parameter set of scalars in the theory, and they were not all gauge equivalent, they couldn't have been because there are only 6-parameter gauge, 6 numbers in an arbitrary SU2 and SU2. So, they were not all gauge equivalent. The only exactly marginal deformations away from this point, there's only one parameter set of exactly marginal deformations away from this point. Okay? Given by changing the size of the circle. Is this clear?
This is an argument interpretation.
Yeah, this is an argument of perpetuity. But to the extent that
I don't know whether
it's true. It's an argument of perpetuity where in general will not be true non-perpetuity. For instance, giving more powerful arguments to check that coupling constant effects don't spoil this. But for instance, the Bologna string will be spoiled by the fact that there's Casimir energy exists. Casimir energy in space-time is a function of certain radius. So there's an effective potential in space-time once you've been constructing quantum effects in space-time that depend on the certain radius. So there's a potential developed for the certain radius. Okay? So in general, I mean, in a situation like this, there will be an effective quantum potential for this function. However, we will be studying situations largely in the superstring in which the space-time theory is superstring, in which we have arguments to show that all these are exact. Okay, but in the context of the Bosonic string is correct, then these are wrong. Because as a matter of conformal field theory, let's say we're interested in exactly bounded definitions of conformal field theory. You can ask from the SU and SU point, what are the possible SU2, exactly bounded SU2 definitions of this is necessary and sufficient. Is this clear? Okay? We would expect there to be some construction because this is not. What?
We would expect there to be some coordinate variable that would influence
In general, yeah, and in the case of circuit of application, as I said, the potential is simply the Casimir energy. What is the vacuum energy? As a function of certain size. Vacuum energy, that's Casimir's calculation. Okay, and yeah, okay. Well, it's true. If the certain size was small enough, there will also be contributions from that. Sorry. So suppose we were at large circle size, the field theory Casimir energy calculation. If we were to be at smaller circle size, what we have to do is basically the calculation of vacuum energy in string theory. The one loop.
Because the Casimir energy alone cannot stabilize.
No, I'm not saying stabilize. The Casimir energy in general indicates a runaway. It gives you a runaway to small circle size. But there's no claim that this can get stabilized. Again and again, I want to emphasize that we study the bosonic string. Basically, they have a relatively technical simple system to mimic effects that will happen in the theory of real interest. The theory of real interest will have supersymmetry. And that supersymmetry will guarantee stability of these circles and modules. So that there will be no vacuum potential. Okay, good. I think that's all I wanted to say about this. Perhaps the last thing to say is I mentioned before that moving away from self-tuned radius is a Higgs field. Okay. The other gauge goes on to become massive as constants of the Higgs phenomenon. It should now be completely clear, right? Because the operator that moves you away is Jz and Jz. So it's charged in the Z component of the SU2 and the Z bar component of the SU2 bar. Okay? So any gauge boson, from the point of view of space-time, it would be depending on a vacuum expectation value of the field, which are charged in the Z and Z bar. So all gauge bosons that do not commute with the ZZ bar direction, and are charged under the ZZ bar direction, will pick up mass. These are the two W bosons of each gauge group. Whereas gauge bosons that are not charged under this direction will not pick up mass. And these are the two gauge bosons. Exactly. The G and B gauge bosons that exist at every value of the certain factor. Okay? So this phenomenon here, from the point of view of space-time, is just a standard instant. Okay? Good. Fine. Okay, so sorry, that's the end of my rewind. Let's get back to it. Okay, so now we're starting off. And we're trying to understand this worldsheet theory gauged under this symmetry expression of physics. Okay, how do we start this? So as I was saying, there are two effects. Firstly, gauging imposes a projection that all physical states are singlets under this symmetry. Okay? So, all physical states execute under the symmetry. Now, let's see what it does to the vertex operators. For instance, suppose you've got del x, del 30 x times e to the power I kx of the this is the vertex operator of the theory without negating some number of insertions. X goes to minus x gives you a factor of -1 for each one of the oscillating excitations. And it flips the sign of k. Okay? So, what it does is give you a factor of -1 to the power number of oscillators. On k, so the symmetry operation on some number of oscillator excitations on k is equal to -1 to the power number of oscillator excitations times the same oscillators and then acting on noise. If we were working, if we were working with circle multiplication, we would have kn and kr separately. Each of them would get flipped, which is the same thing as flipping both n and r. N and r. Okay? Fine. So that's sort of easy. And if that's all there was to it, we'd be very happy. Right? And this is a very simple effect. You just take this conformity theory that you started with and project to the sector that is invariant under this. That is, you take either even number of oscillators and momentum plus minus momentum plus negative momentum, or odd number of oscillators and momentum minus negative. Okay? So, that would be the projection that you would impose onto the theory and we'd be very happy. But, as for the case of circuit compactification, there's an additional effect. That is, when your field goes around from 0 to 2 pi in the string, it can come back to itself, not being periodic, but having x goes to -x. Okay? So, let's say that the names, this projection is the usual projection when you impose any gauge symmetry. But having a new sector in your theory with new boundary conditions, such sectors are called twisted sectors. So winding sectors are an example in a more general overfold theory, what are called twisted sectors. And this particular overfold, namely x goes to -x, gauging by that worksheet symmetry, will have its own twisted sector. So first thing we want to do is to study this other twisted sector. Okay? So let's go back to our first couple of lectures on string theory, where we studied the quantization of string. Okay? So, we've got the same wordsheet theory, the same actions, and same solutions to the equation of motion. So, as then, what we have to do is to expand x. You remember what we did then was to say that we had some an e to the power I n sigma plus bn e to the power minus I n sigma minus. We started by noting that this was the most general solution to a string moving with periodicity from 0 to 2 pi. And we also noticed that periodicity demanded that these n's be integers. Okay? But now the boundary conditions that we want to impose in this twisted sector is not that x go to -x, and it's not that the x is periodic as sigma goes from 0 to 2 pi, but that x is periodic. Okay? So we do that. We can do that by modifying this very slightly. Modifying more expansion to be sigma an e to the power I n plus half. Okay? As sigma goes from sigma to 2 pi, each of these exponents makes up a minus. There's no 0 mode. There's no 0 mode in you see, if a string has to go begin at x and go to minus x, then there's a preferred point. Well, then its center of mass is at x. Right? So a center of mass is not moving anywhere. Okay? Whereas if a string starts at x and goes to x, that x can be anything. It gets its preferred point, x equals 0. And these twisted vector states are localized around that preferred point. Okay? Very good. Now we're going to fast forward to our quantization of the string, the quantization we performed in the first few lectures. Of course, you remember that everything basically goes through, except we use this expansion. Okay? And there's no 0 mode as required. Else it's all states. Okay? But the one thing that we have to take care of that's different, okay, is what is the Casimir energy of the vacuum in this. Okay? So let me remind you. Earlier in our course, we did the following sum. We did sum over n is equal to 0 to infinity, and we found that it was minus 1. It's quite a surprising statement, but let me remind you how it works. Huh? Well?
You put the cutoff function and then...
You put the cutoff function? Let me remind you how we got it, and then I'll derive the modification. Okay, so what we did was to say that, well, first let's look at, we divide this by L, and we get 1 by 12 L, that's much, and L is the infinite string. Okay, so what we did was to say that, look, because N is equal to 0 to infinity, let's multiply it by N divided by L, and put some cutoff function, N by L lambda, where F was some function that was 0, some range of comparable to unity, that, it's like a step function, but a smooth step function around unity. Okay, this was a UV cutoff. N by L was momentum of output. Okay, so this was the UV cutoff on the worksheet of the string in momentum space. Okay, then we used this nice formula, somebody's Euler-Maclaurin formula, which said that half of f0 plus f1 plus fn up all the way to infinity is equal to integral from 0 to infinity f of x minus 1 by 12 f prime of 0 and plus higher order derivatives that turn out not to be true. Okay? And how did that happen? We then just put in what our, let's call this g of x. We put in what our f was. The first f, this half, the fact that we have half here didn't matter because f of 0 was 0. Okay? So we got integral 0 to infinity of x by L, f of x by L lambda. Okay? Minus 1 by 12. Then the only derivative we could take was the derivative acting on x here, because the derivative of this function was just easier. Flat. Or anyway, the powers of lambda would give it. Okay, so we got 1 by 12 L times g of 0, which was 1. So that was that. And this thing, if you remember, this integral takes the form L times lambda squared times lambda. Okay? So the that integral term could be cancelled by a local cutoff, by a local counter term. Okay, it's proportional to L, so it's proportional to the volume of our space. The lambda square is the value of the counter term, the lambda square is the number is the value. Okay? And so what the part that could not be cancelled by a local counter term was minus 1 by L, and that was the physical answer. Now let's redo this calculation in the situation here. What do we have here? Once again, the kind of thing that we'll be interested in is where does this n by L come from, by the way? It was the vacuum energy for each of the oscillators. Okay. So, sum over n by L will, in this situation, now be replaced by sum over n plus half by L, and n will run from 0. And now this calculation is surprisingly more subtle to do correctly. Okay, so let's try to do it carefully and do it correctly. So first thing is mimic all these steps. Okay, so we get integral of x plus half by L times the g of x plus half by L lambda. Okay. X is running from 0 to infinity. Then we get that, but we get that for this sum which has half.